Hi group, it's Mrs. Schaus, here to take a look at section 4.1 on exponential functions with you. We are going to just take a look at this one section prior to break. You're not going to have an assignment until we come back from break, other than to watch the video and respond to the questions within. I want to make sure that we're using all of our time wisely, since, of course, this year, we're struggling to stay up to pace. So even though I know some of you maybe were hoping that we would, take a break a day early, I really want to leave you with no homework, but still use our time wisely. All right. Also notice that I did skip over chapter 3. That's something that we'll come back to later. But I wanted to go ahead and take a look at chapter 4 because it's a little shorter, hoping that we can get this in, or at least the majority of it, prior to ending the semester. Okay, so what we want to do for today is take a look at graphing an exponential function, write an equation for an exponential function, and also be able to use those functions in real situations. Now, exponential functions are something that you should have studied in Algebra 2, but because we ended the spring in a non-traditional way, I'm not sure whether or not you really had time to look at these functions. So I'll try to introduce it as though, perhaps it's new to us, okay? Exponential functions, or at least the parent function, is of the form f of x equals a to the x power. Now, per what we did in chapter 2, you folks know that there could be transformations that would happen to this parent function. We could multiply in some way to imply a dilation, or we could, add or subtract to the x or to the whole function to imply some shift, or again, apply a dilation, or a reflection, right? So some of those kinds of things we'll end up seeing later. But for now, the parent function, f of x equals a to the x power. It does require that a is positive, it's greater than 0, but also not equal to 1. Let's think about that for just a minute. First, by thinking of a different function that we're familiar with, power functions, that family of functions. So if I look at something like y equals x squared or y equals x cubed, we're kind of familiar with those. How is this different when there's still some kind of, exponent kind of thing going on? Well, if you look at the functions y equals x squared or y equals x cubed, the x is the base, and we have a constant number that represents the power. So here that's sort of reversed. The base, the a value, is a constant number, and the variable is the exponent. So as we look at that function, we'll be putting a variety of different things in for x and seeing what we get out as a result for the y values. Now, if we were to have a base of 1 here, then think y equals 1 to the x power, then no matter what value we put in here for x, we would end up getting 1 as an output, okay? And so then essentially nothing changes, right? That just becomes the function y equals 1, right? We wouldn't even need to write the power then, right? Okay. All of these types of functions will have a graph that passes through the point 0, 1. Well, how does that make sense? Okay, no matter what this a value is, it could be 2 or 3 or 7 or 2/3, right? But something greater than 0. Then if we raise that to the 0 power, remember, any non-zero number to the 0 power is 1. So we would get 1 as the output. So all of these, and again, that's without transformations, will pass through the point 0, 1. Also, they all have the x-axis as a horizontal asymptote, which you'll see in a minute here when we take a look at some of the graphing. When the a value, or this base, is greater than 1, that means that we're increasing or experiencing some type of growth. When we get to applications, you'll see things like population growth, or our money growing when we invest it in a compound way, right? And then if our a value, our base, is between 0 and 1, a fraction between 0 and 1, then the function is decreasing, or we call that sometimes decay. And again, maybe we would look at something like radioactive materials that decay over time. All right. For all of these, the domain is going to be the set of all real numbers, and the range, again, without transformations, the range would be bigger than 0, again, because our x-axis is the asymptote, so strictly bigger than 0, not including the 0, to infinity. All right, so let's take a look at a couple of graphs just to get a feel for the shape of the curve. Again, I'm not going to graph specific functions here. I just want to, try to make some of this a little bit clearer to you. So if our function is a greater than 1, again, meaning our base is bigger than 1, we had said that that was representing growth here. And so passing through the point 0, 1, as all of them will do, what we're going to see is that working from left to right, this is going to start out with some very small values, pass through that point 0, 1, and then it's going to increase very quickly, actually, because it is, in fact, exponential growth. It'll go up quite quickly. Again, this is not representing a specific function, just the shape of that curve. But what I should notice is that as I work towards the left, this curve is getting closer and closer to the x-axis. It will never pass over it. Again, parent function without any shifts. Okay? And so maybe I should write not only a is greater than 1, but that it is representing growth. All right, then when our a value is between 0 and 1, representing decay, that is when our values at the left start higher and they're coming down. They'll still pass through this point 0, 1, and they will approach the x-axis, getting closer and closer to it, but again, never actually crossing over it. And like I mentioned, starting up higher here. So I'll have a similar shaped curve. It's coming down here, getting closer and closer to that axis, but never passing over it. Now, sometimes what happens is folks will try to get closer and closer to this, and then in order to draw in the arrow, the edge of the arrow will come over the line, and I'm okay with that, but just make sure that your curve doesn't actually come over the line. Again, talking about parent functions without any shifts, okay? Oh, I wanted to mention too, before we do move on, this business of domain and range. So notice here that the domain being all reals, it means that this is going to continue on as the x's get smaller here or as the x's get larger here. I've got arrows on both ends, right? So all real numbers for the x's, same thing over here, all real numbers for the x's. But notice that since it sits above the x-axis, all of our y's, or the range in other words, would be not including 0, but working upwards, so towards infinity. All right. Now with that in mind, let's do some things. Let's graph the function y equals 2 times the quantity 1/4 to the x power. Maybe we should take a minute to talk about, is this an exponential function? Well, absolutely. We've got a base here that's greater than 0, not equal to 1. It's raised to an x power. The multiplication out front really implies a dilation. But here, they're not asking us to consider the dilation as a way to graph. They do want us to simply make a table of values. So all I need to do is plug in some values and see what I get for outputs. Well, let me plug in that -2 here for x. Maybe you need a recall that when we have a negative power like this, it means to take the reciprocal of the base and make the power positive. So this is really that's not 1/4. It is really 4/1, or 4 raised to the second power, and that equals 16. So now if I multiply 2 times the 16, I get an output of 32. So I need 32 here. Let's do the same thing with the -1. Take the reciprocal of the base, that becomes 4 to the first power, or just 4, times 2, that gives me an output of 8. Plug in 0 for x. Any non-zero base to the 0 power will give me 1 as an output, and then times 2 will give me 2. If I plug in 1, I get 1/4 times 2. That would give us 2/4, or a half. And if I plug in the 2 here, I need to square a 4th. That would give me a 16th. And then if I multiply by 2, 2/16 will reduce down to an 1/8. All right, if I'm going to think about trying to plot those points to create the graph, I think I'm going to have to use intervals bigger than 1 here. Probably, let's see, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. That'll give me 20. 2, 4, 6, 8, 10. That'll give me 30. Yeah, and I need to be as high as 32 here. I'll go ahead and use intervals of 1 on the x axis, however. So to plot the point -2 and then 32, that would take me up to this point right here. And then the point -1, 8. 2, 4, 6, 8, I'd be right there. And then to plot the point 0, 2, I would be here. The point 1 and then a half, I'd be, remember, if this is representing 2 units, I wouldn't even be halfway up. I'd be a quarter of the way up. And then 2 and 8, oh my goodness, I'm just barely up off the x-axis, right? So I can see that this is definitely approaching the x-axis, and I'm going to have these little bitty fractions over here if I were to continue onward, but it won't ever, whoops, looks like it turns back up, but it won't ever become 0, right? It's just going to, kind of ride along the edge of that x-axis there, and because of the thickness of my pencil, I'm having trouble even drawing that in, aren't I? And then I'll try to get these other points here that we had mentioned. So not a perfect graph, but a reasonable sketch. All right, one thing that I definitely wanted to mention is that this does not pass through the point 0, 1. It passes through the point 0, 2. And you might go back and say, well, Mrs. Schaus, you said all these functions pass through the point 0, 1. But remember, I said that was for all the parent functions. This graph has been dilated, right? It's a vertical stretch by a factor of 2. So my point 0, 1 got multiplied in the y-coordinate by 2 and became 0, 2. Well, this is connecting right into the content that we just left from chapter 2. Okay. The other thing that I would note is that this is a decaying function, in the sense that it is starting out with higher values and dropping, quite quickly. And we, again, expect that to happen when this base is between 0 and 1. All right, so consistent with what we've been saying. All right, let's take a look now at a couple more graphs, but this time, instead of just making a table of values, they want us to use the idea of transformation with a known exponential function as a way to graph. Now, true enough that maybe we don't know what the, sort of initial or parent function looks like, so we might still need to make a little table here. But I want you to think about how you could use the idea of transformations to graph these. So I want to start out here with the parent function f of x equals 2 to the x power. No plus 3 business, that's representing a shift. I think we know that, again, from just leaving unit 2. So let's make a table of values here to graph this parent function. Maybe I'll pick a couple of negatives, 0, and a couple of positives, and see what we get for outputs. If I plug in a -2 here, take the reciprocal of the base 2, which then is going to give me a 1/2 to the positive 2 power. Well, a half times another half would give me a 4th as an output there. Let's plug in the -1 for x here, 2 to the negative first. Again, the negative means take the reciprocal, so I would just have 1/2 to the first power, or just a half. 2 to the 0 power, 1. 2 to the first power, 2. 2 to the second power, 4. And so I'm going to go ahead and graph those points just to have the initial parent function sitting on my curve. All right, or sitting, on my graph. So let's do -2, again, up a 4th. I'm going to go ahead and try to use units of 1 here because I have relatively small outputs. So -2 a 4th, again, barely up off that graph. -1/2, again, I'm just, halfway in between 0 and 1 there. I'm passing through the point 0, 1, the point 1, 2, the point 2, 4. And I don't know, maybe I should have put in another point. Maybe I want to do, let's see, 2 times 2 is 4 times another 2 is 8. That's 3, 8. Maybe I'll plot that. 3, and then that was 4. This will be 5, 6, 7, 8. I'd be right there. So let me, again, just go ahead and graph that. Maybe I'll try to make it look sort of dashed, if we will, to look like our parent function. This plus 3, notice that's being added into the x, not added afterwards, right? Added into the x. So what type of transformation is that? Oh, that stuff from chapter 2 isn't going away, is it? If I'm adding into the x, that means that it is a horizontal shift. Remember that horizontal variable kind of works counter to what we would think. So this plus 3 really means we're shifting 3 not to the right, but instead to the left. So we're going to take all of our points here and we're going to shift them 3 units to the left. And so you could, maybe physically take this and go 1, 2, 3, move that point. Take this and go 1, 2, 3. Here, 1, 2, 3. The same thing here, 1, 2, 3. And that would give you then my new transformed function. So I'll label this one, maybe down here, as g of x, and this one as f of x, right? And you can physically see that shift over 3 units to the left. All right, let's take a look at our h of x. What's the parent function here? So I'll label that, let me call it maybe the parent function here, j of x. It would be 1/2 to the x power. What does that negative represent? It represents a reflection, okay? All right, we'll talk about that in a minute. Let's go ahead and make a table of values for our j of x here. And again, maybe I'll pick a couple of negatives and 0 and a couple of positives, just at least to start us out, see what that gives us. All right, if I plug in -2 here for the x, the negative means take the reciprocal. So my base becomes 2. 2 to the positive second power then is 4. -1 for x. When we take the reciprocal because of a negative, we get 2 to the first power or just 2. If we raise it to the 0 power, we get 1 as an output. Raising it to the first power, I just get a half. And raising 1/2 to the second power would give me a half times a half or a fourth. All right, let's go ahead and plot those points again just to think about what the original parent function would look like. So -2 and then up 1, 2, 3, 4 would sit here. -1 and 2 would sit here. 0 and 1, 1.5, and then 2, a fourth, again, just barely up off that axis. Boy, maybe I should have put a -3 in here. It should sit up here, but let me add -3 into our table so we can come back here a little bit. If I raised a half to the -3rd power, the negative would make the base a 2. 2 to the 3rd would give me 2 times 2 is 4 times 2 is 8. So let's go ahead and plot -3 and then 1, 2, 3, 4, 5, 6, 7, 8. I'd be sitting right there. That gives me just a little nicer feel of what this curve should look like. And again, I'm going to kind of try to make it look dashed. Put my arrows on the ends. And in a minute, we'll label that as j of x. But now this function h of x equals the opposite of 1/2 to the x power. Because this negative is not attached to the x, it sits on the outside, we're taking the opposite of the whole function value, which means we're taking the opposite y value. And that represents a reflection through the x-axis. Okay, so I'm going to take this point that's at -3 and it's up 8, and I'm going to do a -3 and then come down 1, 2, 3, 4, 5, 6, 7, 8, right there. And similarly, the point -2, 4, I'm going to do -2 and then down 1, 2, 3, 4. -1, 2 will become -1, -2. 0, 1 becomes 0, -1. And these points that are close to the x-axis are still going to draw in towards the x-axis, but just from the opposite side. Okay, so I have a graph that looks like the following. Now, you might say, yeah, but if you got to make a table anyway, why wouldn't you just make the table to fit this new function? Well, perhaps this would have been given as j of x, and then you would be asked to graph this, and it would be super simple to just think about reflecting those points through, okay? So I'll label this one as our final function, h of x, that we were looking for. Awesome. So that's it with regards to the graphing piece. let's now kind of switch gears a little bit and take a look at writing an equation of this particular form, y equals a to the x power. Now, note that at some time we may take a look at a function that has been transformed in some way. If there was some, let's say, dilation, there could be a multiplier kind of sitting out in front here. And I might ask you to write the equation of the form f of x equals c times a to the x, something like that. But for now, we are only talking about parent functions and trying to write the equation for it, okay? So what you should do is look at the graph, and other than the point 0, 1, you want to find another point that sits on the graph. So we're identifying this point as being 364. Maybe there would be, other points that you potentially would be able to use. But I'm going to use that point 364 as a way to go ahead and write this equation. And keep in mind that function notation could just be written as y equals a to the x power. And I like that because I want to be able to think about plugging in this xy point into my equation to find my unknown base. All right, so I'm going to plug in 3 for the x and 64 for the y. So now I'll have 64 equals a to the third power. How do we solve that? Well, we simply take the cube root on each side. Since the cubing and cube rooting undo one another, we'll have our value of a, which would be 4. All right, if I know that the a equals 4, then the function I was actually looking for is f of x equals 4 to the x power. So it's pretty simple. Similarly here, I have another function that contains the point 4 and then fractionally 81/16. Well, that's all right. I know that my function is still going to have this same form, y equals a to the x power. I'm going to plug in 4 for the x and 81/16 as a fraction here for the y. I do want to leave it as a fraction, and I think you guys probably see why, but it's not a nice value. I would get, some extended decimal there. So if I leave it in this form and now think about solving for a by taking the fourth root of each side, okay, do we know the fourth root of 81? Well, that's 3. And do we know the fourth root of 16? That's 2. Whoops, I forgot my fourth power here. And again, that fourth rooting and fourth powering undo one another tells me that a equals 3/2. Now, some of you might say, if you take a fourth root or an even root, could this be a positive or a negative? But note that this is sitting in the upper quadrant here and increasing, so it makes sense that we're going to have that positive base. So we really are just looking for y equals 3/2 to the x power. And I could have written that as f of x, of course. Same thing. Okay, so that's a little bit with writing our functions. The very last piece is we'd like to be able to apply the idea of using exponential equations in some real setting. Okay, I want you to recall the compound interest formula. And I say recall as though we have seen it before. I believe we have, probably even in Algebra 1, if not in Algebra 2. Okay, it says a of t equals p times the quantity 1 plus r over n, and that is raised to the n times t power. Well, this might be a point where if you're not familiar with that you pause and write down what these variables represent. So a is the amount in the account or in the investment. Okay. P equals the principal, the original amount that was invested or put into an account. R equals the rate. N equals the number of compoundings per year. And T equals the time. And maybe, I wasn't super clear in all this. I probably should say that R is the annual rate, and I probably should say that T is time in years. So if you want to be more specific, definitely feel free to write that in. Okay? All right, so it says if $6,500 is invested at a rate of 8% per year, compounded quarterly, then find the value of the investment after each number of years. Well, we know that that means with 6,500 being invested, that is our principal value that we're starting with or putting into the account initially. The rate is 8% per year. When we think about the rate, however, I do need to make sure that I'm putting it into the formula as a decimal equivalent. So I'll write that in as 0.08. I also need to know something about this compounded quarterly business. I need to know what that term quarterly means. And I think most of you probably know, maybe just from talking to your parents or thinking about money in the sense of a dollar in quarters, that means that there would be 4 quarters in the year. And the times are given down here in parts A and B. So that would be everything that we need to plug into the formula in order to find our new amounts. So let's take a look. And notice also, I'm going to pop back up here for just a minute, that this formula says A of t. That's because we're writing the function with an input of time. But really, the formula could just say A equals, because the amount, if we left time constant, could be a function of the number of times that it's compounded per year, or as we change the rate. Okay, so the fact that I'm writing it as a function of time is just a choice. Okay, all right, so the amount based on 4 years would equal 6,500 times 1 plus 0.08 as the rate, divided by 4 for the number of compoundings. And here, be careful, this is n times t is the power. So I've got to do 4 quarters for n times 4 years for t. So that's really a 16th power. All right. And at this point now, I let the calculator do that work for me. So I'm going to grab my calculator. So you can see it in the screen there. Okay, there we go. All right, and I'm going to plug in 6,500 and then in parentheses 1 plus 0.08 divided by 4. I'm going to close that parenthesis and now raise that to the 16th power. Now I did the 4 times 4 in my head, not terribly difficult to do. If you had one where this wasn't as simple, you want to make sure that you're thinking about putting that in parentheses. Perhaps you have a calculator that'll stay in the exponent until you use the arrow key to bring it down. But you want to make sure that you definitely are aware of how you're entering that into the calculator that you're using. All right, so that gives me $8,923.11, rounding to the nearest whole cent. Notice that doesn't answer the question, how much interest did I earn? It answers the question, what is the new amount in the account? Right? What's the value of this investment? Okay, let's take a look at A of 6. So the 6,500 is going to stay the same. The rate of 8% is going to stay the same. The frequency that we compound quarterly is going to stay the same. But what's different here is the time, 6. So once again, we'll go ahead and plug in 6,500 times the quantity 1 plus 0.08 divided by 4. Close that up. Let's raise it to this is a 24th power, and see what we get. $10,454.84. All righty, let's take a look at another style of application, populations. Okay. In this particular scenario, a certain fox population of 220 is released in a region and begins to grow at a rate of 18%, probably should say per year. This growth rate continues for 12 years. Write an equation to model this exponential growth and use it to predict the population for the number of years indicated in the table. All right, so we want to write our equation thinking about our outcome equaling what we started with, but then now increasing. Now keep in mind, if it's increasing at a rate of 18%, we need to multiply by 1.18. The 0.18 will, like add in the growth, if you will, but keeping the 1, multiplying by 1 gives us the original population that we started with. So 1.18 will actually be our base in that case. All right. And then again, we're using our x as the exponent. Now, because this function is dealing with time, right, number of years, perhaps we would prefer to write it in function notation and write it as f of t equals 220 times 1.18 raised to the t power. Because, in a context sense, using t as the input variable choice might be better, right? All right, so I'm going to plug in 2 years for the amount of time here and see what we get as a new population. And then we'll do the same thing for 5 and for 12. But we're going to let the calculator do that work for us. So let's do 220 times 1.18. We're going to raise that to the second power. And we'll get, now we're going to approximate here, approximately 306. And I'm just going to do to the nearest whole. We know we can't have fractions of fox in our population. If it's a fractional fox, it's probably not really alive. Okay, let's plug in the 5 here. So I'm going to do 220 times 1.18. We'll raise that to the 5th power, and we get approximately 503. And for this last one, 220 times 1.18, let's raise that to the 12th power, and we get 1,603. 1,603 fox after the 12 years. Now, some of you might have been wondering why I said this growth rate continues for 12 years. Like, why did I put that in here? When we write a model that represents something like population growth, we do need to make some type of statement or prediction or something about how long we believe that model will hold, or maybe we're not even sure. But what I can tell you is that the model won't hold indefinitely. And I think that's pretty obvious. It won't hold indefinitely because, eventually there'd be something like scarcity of food. Okay. So knowing that it held for 12 years told me that I could make an assumption that plugging in these values would give me a reasonable approximation for that fox population. All right, folks, we're at the end of the video, and I just wanted to make sure that I said happy holidays to you all. I hope you folks take some time to relax and enjoy, and I'll see you back, hopefully refreshed and renewed in the new year. Talk to you soon.